warm in here.
It feels like a bath.
It went up like 5 degrees as soon as I crossed the threshold of the doorway.
Yeah. It feels like a bath to me.
Mm.
So there's this like sweat smell in the air.
Yeah.
But it is there. So
Yeah, thank you.
okay. Huh?
Showers are usually a lot warmer, and I like the super hot showers.
Same here.
I had my water go out the other week, and I had to force myself to take a cold shower because it's terrible. worst decision I ever made.
Especially in the we are still in the winter, right? So in the winter, a cold shower is not the worst thing, but one of the worst things that can happen here.
Pipes are like near freezing.
Yeah, yeah.
So it's just like...
There are some people in Russia that like go to Siberia in the winter to take cold baths.
I don't think I could.
Yeah, same here. So, ready? Are you ready for the orbital?
Yep.
How do you feel about the topic so far?
I'm excited. I like all the rocketry stuff and all that. I was pretty excited about Untitled Chapter.
Yeah, that's.
I may not be able to remember and answer every like math thing, but off the top of my head, but
That's all right.
yeah.
That's understandable.
So if nobody else shows up, can I get a bonus point for being a good student?
What time is it? Wow. Oh, okay. I guess you can. Why not? I'm very generous with the bonus points, aren't I?
Yeah, you gave us 20, you give us 20 love.
Okay. Yeah, the other day, one of the professors was giving me was actually telling me not to be so lenient.
Really?
Yeah. I was like, I don't think I'm lenient though. It's just.
I wouldn't say not. You're very understanding.
I appreciate that.
Some circumstances when they come up.
I really appreciate that. So, Steven is also here. Yeah, we only have 2 students. What should we do? Should we wait or should we go ahead and start? Okay, I'm gonna give Steven and Trey a bonus point for being on time, I guess. For doing what you're supposed to do, but no. We don't have mandatory attendance policy, so I will definitely give you a bonus point.
Because people are scared of the weather.
Oh yeah, that's.
I was gonna go back to my apartment after this class because I just want to make sure in case anything happens, I guess. But
Yeah.
I was gonna tune in online.
I have to teach the class, my other class, fluid mechanics. Okay. My other class is at 2:50, so it's definitely during the storm.
I think that's like the apex of when it's supposed to happen.
Yeah, that's. So, okay, but I guess we die if we die, right? There's nothing we can do about it. Okay, so I guess we can go ahead and start. We're already 2 minutes in, 2 or 3 minutes in. Let's finalize what we were doing for the last lecture. That was, Nicholas, you should have came in like 2 minutes earlier. You would have gotten a bonus point. Yeah, that's just 2 or 3 minutes earlier. You would have gotten a bonus point. So we talked about the relative velocity, all of the like time derivative of a moving vector, and then we talked about how it applies to something that is moving on the over Earth, right? We had all the formulas. I'm just gonna rewrite some things. That's some of the formulas that I don't remember if we covered. So the v relative of whatever that is orbiting around the Earth is going to be equals to x dot I, y dot j, and z dot k. This is something we talked about, in which x dot is equals to re, the Earth radius, plus z, lambda dot cosine of phi, and y dot is equals to re plus z phi dot. And z dot is the speed at which you are moving away from the Earth's surface, right? You can rearrange these formulas to actually get the values for the changes in angles. Lambda dot and phi dot can be equal to x dot divided by re plus z cosine of phi. Phi dot is equals to y dot re plus z. Okay. Since we are also interested in acceleration, it's not a bad idea to get the second derivative with respect to time of all of these things. So I'm just going to write down the equations for you. And I'm sorry that these equations are very long equations that you will probably not use. But we have to go. But we just have to go over them. So just bear with me. Okay, that's phi double dot. How do we calculate phi double dot here? With respect to time, that's it. And the things that are changing here are y dot and z. You're taking a derivative of a ratio, right? Which essentially means that take the derivative of the numerator multiplied by the denominator minus the derivative of the denominator multiplied by the numerator divided by the denominator by 2 squared, right? Okay. And we do the same thing for lambda to get the lambda double dot. It's going to be equal to re plus z x double dot cosine of phi minus. So what should happen here? Actually engage with these equations a little bit. So this first term was the derivative of the numerator multiplied by the denominator, right? So we already have that. What should happen to the second term? So the question I'm asking, I'm sorry. The question I'm asking is that what is the derivative of this?
It's going to be product rule. It's going to be sine RE plus the times the derivative of the inside, which is it's taken with respect to t. Or not t.
It is taken with respect to, right? This is the second derivative with respect to time. Okay.
So it can just be multiplied by RE plus z.
RE plus z. Okay. What you're telling me is that you have to take the derivative of this first, then multiply it by this, then take the derivative of this multiplied by this. That's what you're telling me, right? Yeah. That is essentially true. And let me actually, in my notes, I have the final version of it. So let me just give you the final simplified version of whatever we have. It is going to be z dot cosine of phi minus, and something that it is worth mentioning here is that, or maybe I can ask you this as well. What was the derivative of cosine of phi with respect to t? Negative sign, not sign. You said sign. That's all right. I just want to make sure that you are clear on this. So a squared. Psi dot, phi double dot, and lambda double dot. Phi goes in, you get the value. So based on this, we can actually find the relative acceleration as well as the derivative of v relative. It's going to be x double dot I, y double dot j, plus z double dot k. What should be the next three terms? That's all right. You just keep copying. You don't have to. But we have enough time. So whenever you're done writing, we want to find the acceleration, right? We want to take the derivative of relative velocity with respect to time, right? You take the derivative, you're going to get double dot, y double dot, z double dot, and what is the rest of it? The rest of it is x double dot, derivative of your unit vector with respect to time, right? That was the idea. It's a moving frame. Okay. And again, it's a moving unit vector, so the magnitude of this unit doesn't change. Derivative of I with respect to time is going to be equal to I, the vector itself, cross product of the angular velocity of the frame, of that vector, right? That was the idea. So you plug that in, you plug that concept in, and you simplify the equations you're going to get. And this is the final equation you're going to have for relative acceleration. This is the relative acceleration of something that is moving around Earth, right? It's a very long equation. And it's usually you can usually simplify this to a smaller format equation. But we should see the long format at least once in our lives, right? That's the idea. I and y double dot plus y dot z dot, the tangent of phi divided by re plus z j. And the last term is going to be z double dot plus z dot k. This is your relative acceleration. Okay. Eventually, this is what I mean is, we are only looking at the relative velocity and accelerations. So the absolute velocity is going to be even more complicated, right? It's something we have seen before. But I have one question. What will happen to these equations? What will happen to relative acceleration if the Earth's curvature becomes infinitely large? Before answering that question, what does it mean? What does an infinitely large Earth curvature mean for the movement of whatever that is moving around the Earth? the radius is infinitely large, right?
Does that mean the acceleration of the object? No.
It's not going to go to 0. But what does it mean for the Earth's surface? When you have a very large radius, essentially a small curvature. Did I say large curvature? I meant very small curvature, right? So very large radius. What does it mean for the Earth? This essentially means that if you assume that the Earth radius is very large, this means you have joined the Flat Earth Society, right? That's the idea. Radius is very infinitely large where you're dealing with a flat Earth, right? So that's an assumption we can make, right? It is not a very, it depends on your flight and all of those things, but this is an assumption we actually do make. So what will happen to this equation if we make that assumption? An infinitely large radius. So you have to plug in infinity here, 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 right? What does it mean for acceleration? That's it. That's it. That's it. Okay. And if I ask you to find the final absolute value of acceleration, just have to go back to the equations we derived in the previous lecture, which is the velocity of the center of the Earth, where we have the inertial frame, right, located on, and angular velocity of your frame of reference that sits on the same inertial frame but can rotate, right? That's the angular velocity of Earth multiplied by the relative R relative. That's the cross product plus V relative, right? So far, the only thing we have calculated is the relative velocity. So you have to make sure you have the R relative, omega, and all of those things as well. And you actually had, from the previous lecture, you had a bonus point to calculate acceleration too, to get to the acceleration equation from this velocity. But I'm going to just write down the acceleration equation. Give me the acceleration of the center of the Earth, whatever that is, plus the omega dot divided by relative. Just have to take the derivative with respect to time. Okay, and then plus A relative. This part will become eventually all of these are vectors, just to make sure that you're plus 2 omega, very large. What will happen to this equation if your angular velocity doesn't change with respect to time and your acceleration of the center of the Earth is 0? What will happen to this equation? It will be just the last 3 terms, right? The 2 on the top plus whatever the relative area is that. We can actually plug in the values we have for the omega and all of those things to find that even the larger formula for acceleration. We are not going to do that, but the equations are mentioned in the book. And actually, I wanted to show you the equations, so I don't want to write them down. Let me use the overhead here.
Earth, you only have to deal with the last three terms?
No. That's not a flat Earth assumption anymore. You're just assuming you're asking about that equation, right? When you assume flat Earth, your radius of the Earth is going to be infinitely large, right? But over there, we are assuming the center of Earth. If you're dealing with this flat Earth, even flat Earth society people are saying that it is a circular Earth. So you have a center, right? The center can accelerate and can rotate around itself. That the rotation can still be there, right? So those two are zero because we are assuming the Earth is moving at a constant velocity and is rotating at a constant angular velocity. Okay. So if you plug in the values, I hope you see these equations here. I'm talking about the equation of A. All of these. This will be the final value for acceleration. Okay, final equation for acceleration. We have all of the terms, all of the popular terms here, the omega, all of those things, and we can make adjustments to this equation. We can actually make it simpler. Let me go to the next page here. Special cases to make the equation even simpler. I'm assuming you see this, right? So for example, if we assume a straight level unaccelerated flight, so v is going to be this, a is going to be this. That's the acceleration. All of this. That's acceleration and velocity relative to an inertial frame of reference, right? In flight mechanics part of the class, we were doing everything compared to the Earth's surface, right? But here, these equations are the equations relative to the inertial frame of reference. Okay, and there are other things. If you don't have the book, I can share this page with you if you need it, but I don't see how you are ever going to need this in this class, at least. Okay, so that's it for the chapter 1 of the book, okay, which is just a reminder of the dynamics. If you haven't passed dynamics yet, this is something that you should see in dynamics. If you have already passed it and you haven't seen these, you have to go back to your professor and ask for your money back. But I'm just kidding. Yes, some people don't cover. But yeah, so for the next chapter of the book, which is going to be the original orbital mechanics, no reminders, no flashback to the other courses, we are going to talk about two-body problem. We are going to talk about the two-body problem. Let me wipe the board clean, and then it can start. So, two-body problem, which is the main part of the orbital mechanics. Orbital mechanics. We are mostly going to focus on two-body problem. If we have enough time, we are going to get there to. Okay, yeah. We are going to get to the three-body problems as well, but that's just in case we have enough time. That's something that you won't really deal with. Well, what is a two-body problem? So chapter 2 of the book, two-body problem. To understand what we are talking about, then I say two-body problem, you have to understand the most important and dominant forces in orbital mechanic analysis. Okay, what do you think that is? The delta what? The most important force. Gravity, gravitational force. What was your answer?
I said
delta V. Yeah, okay. So gravitational force is the most dominant force, and this is for the most part, it is the only force we consider when we are doing a force analysis, force balance analysis for this class. The two-body problem is the motion of the two bodies due due to their mutual gravitational force. So let me write it down. Motion of two bodies due to this, the gravitational force, the gravitational force between the two. So this motion is actually a conic section, which is included in one of the Kepler laws. Hopefully we'll talk about today. So this motion itself is conic section, which essentially means that it can be a circular motion, it can be an elliptical motion, it can be a parabolic motion, or a hyperbolic motion. Okay, so circular, elliptical, parabolic, and hyperbolic. Okay, so the first thing you want to do here is to understand the gravitational force and how can we find the gravitational force between the two bodies. Let's say we have a body 1 and a body 2. What is the gravitational force between these two bodies? The two apply gravitational force to each other. F1 to 2 is going to be equal to this famous gravitational equation formula divided by R2, which is the distance between the two. So M1, M2, and in the direction of the R, which is the distance vector between the two bodies. Okay? And F21 is going to be equal to the same force, just in the opposite direction. When you want to do the analysis, when you want to extend your analysis, what you do is you actually choose a frame of reference, X, Y, Z, and then all of these two have an R1 and R2. That's their position vectors. R1 here is Xi, Yj plus Zk, and R2 is, let's call it X1, Y10, X2i. So the frame of reference we are choosing is going to be the inertial frame of reference. And whenever we use the inertial frame of reference, it's going to be your clue to understand that we are using an inertial frame of reference is using the capital letter for the unit vectors. Okay. So, okay. These two bodies that are interacting with each other are going to have a center of mass because it's a system of 2 point masses. Something that I need to mention here is that we are dealing with a system of point masses, but we can show that as long as these masses, even if they are not point masses, as long as they are spherical, this analysis applied to those spherical masses as well. Okay? Which essentially means that with the assumption that the planets are spherical, we can apply this analysis to the planets as well. It doesn't have to be a point mass. Okay? So, center of mass. How can we find the position vector of the center of mass? We have the position vector R1 and R2. I want to find the position vector R of G. How can I find this position vector? We have two masses, and what I'm asking you is to give me the position vector for the center of these two mass. Just think about it. What would have been this position vector of this? What would have been the location of the center of mass if these two masses were equal to each other? Half vector. So a weighted average, essentially, right? So that is essentially what you said. So R of D, this position vector, is going to be equal to m dot R1 plus m2 R2 divided by their masses. The velocity of this position vector, of this center of mass, is going to be m dot mr1. What is happening with this one? m1 r dot 1, m2 r. I'm sorry about this noise. It's just there's nothing I can do about it. m1 plus m2. Okay. What can we say about acceleration? It's equals to r d dot, right? What can we say about the acceleration of the center of mass? It is going to be r double dot, right? So essentially the same equation, mr double dot plus mr double dot divided by m1 plus m2. Okay. So we have the position vectors of each two masses based on an inertial frame of reference. How would you find this distance vector? Let's call it a distance vector, r, a small r. How would you find that? We have R1, R2. We were able to find the position of the center mass. But here we want to find the distance vector. Let's call it this a small r. Right? How can we find this? And subtract them, right? So your r is going to be R2 minus R1, which essentially means that each component is going to be x2 minus x1, y2 minus y1, and all of those things. And based on this analysis, we can actually find the unit vector in the r direction, which is going to be vector r divided by r, right? And we already know how to calculate the forces. F12, the gravitational force, G, m1, m2 divided by r multiplied by u of r squared. And F21 is going to be negative m1, m2 divided by r squared u of r. That's the gravitational law. That's the Newton's gravitational law. But what would you get? What would we have if you want to write the equation? Then use the second law of Newton's second law and write the force balance for each of these masses. That would be equal to mass multiplied by A, right? Which essentially for F12 is going to be M1 R1 double dot, M2 R2 double dot, right? So we can identify the relationship between the position vector and the masses and how the position vector changes with time, okay? Before moving on, I want to ask you one question. We're not going to prove this, but I just want to see what your opinion is. So what can we say about the acceleration? Let me use a acceleration of the center of mass. These are two bodies, right, that are moving into a space and interacting with each other because of the gravitational force between the two. What can we say about the acceleration of the center of mass?
Acceleration increases as radius decreases.
Acceleration of the center of mass. Only the center of mass here, right?
And this is between the two bodies, right? Because it's the reference frame, right? It's between the two because we were looking at.
The center of mass is always between the two bodies, right? That's
So would it be constant since the two bodies won't be changing masses in the scheme of things? None of these positions should really change if you're thinking about planets and space.
so what you're telling me is that the acceleration is the acceleration constant. What is constant here? Yes, there's no other forces, right? It's just a gravitational force.
Acceleration would be constant. If you're in a vacuum, you have a certain acceleration, you can keep moving that acceleration.
But there is no outside forces on the center of gravity, right? And the gravitational forces at that location, because of the weighted average nature of things, is going to cancel each other out, right? At that speed, right? So acceleration of that point would be 0, right? Which essentially means that based on what Neil said, since there is no outside forces there at the center of gravity, if it's moving, it will be moving at a constant velocity, right? It will keep moving. That's center of gravity, right? But it won't rotate. It will just move at a constant velocity. So the position vector, and for a constant velocity movement, we can find the position vector as a reference position vector, wherever that is, rg naught plus the velocity of that acceleration multiplied by t. That center of mass multiplied by t. Okay. What time is it? So I actually, at this point, I want to solve an example for you. Okay, that's the example 2.1 of the book. That's an interesting, actually, example. I'm going to give you a couple of minutes to think about this, to work on this, and think of this as an attendance quiz. Okay. At the beginning of the class, for those of you who joined later, we only had Trey in class and Steven online. We still only, no, we have a lot of other people online as well. But at 10, I think until like 3 minutes past the class, 4 minutes past the class, when Nicholas came. So I just gave Trey and, what's that? I just gave Trey and Steven a bonus point. I don't even think Steven was listening because there was no reaction there online. Well, he was present, so got a bonus point. But so I think everyone is present, so an attendance check is a moot point. But let's do it anyways because I want you to work on this. We want to use the two-body. Let me read them properly. We want to use the two-body equations of motion, which are these two, right? Two-body equations of motion, to show why orbiting astronauts experience weightlessness But how can you show that using the equations we have here? Just like start writing down the equations for the astronaut and the Earth and see what you're going to get. The first thing you need to ask yourself is that what are the forces that are being exerted on an astronaut that is who is sitting inside a spacecraft and is strapped to a chair, whatever.
Well, the force of the strap.
Contact. We just call it the contact force. So that's one force, right? What are the other forces?
Gravity.
Gravitational force, right? What else? That's the gravitational force on the astronaut, right? There's also a gravitational force on the spacecraft itself, right? So there are three forces. The two forces, the gravitational force on the spacecraft and the gravitational force on the astronaut, are essentially the same force. So they will cancel each other out, and you will get a contact force equals to 0. So the astronaut will get the feeling of weightlessness. That's just a feeling that you feel, right? Doesn't it? Yes.
When most of the proportions of mass of Earth versus the atmospheric spacecraft just be
Yeah, you can look at it from different perspectives in general. But if you want to be too analytical about this, which this orbital mechanics book loves to be, right? Loves to be very too analytical. You have to write down all of the forces. But yeah, at the end of it, something that you are missing here in that analysis is the force of the strap on the body, right? That Neil mentioned. If the astronaut is inside a spacecraft and is strapped, you have to make sure that the forces that the strap is you are exerting on the strap is 0, right? Which you cannot calculate by just saying that your mass is not comparable to Earth and the distance is so much.
well, unless the astronauts move, won't there be no force in the strap?
Pardon me?
If the astronaut's not moving, won't there be no force in the strap?
That's the idea, right?
Yeah. So then why would you model it?
What would you want?
Why would you model it if the astronaut's not trying to put force?
Just a thought experiment. I don't think anyone would want to model this in general.
Just strapped in, the strap.
So that's actually you mentioned an interesting thing. It is 0G, right? So what Neil is telling us is that there is no force being applied to the astronaut because it's 0G, which essentially means that there is no force on the spacecraft as well. Okay, 0G. But the G is the gravitational force constant, right? That's the idea. That is G. Let's say this is the M of Earth. That's what we discussed, right, in the previous lecture. G is this part of it, right? If it's 0, your force is 0. So the orbit won't be there anymore. Okay? G is going to be smaller compared to what it is on Earth. That's for sure. Compared to what it is on the surface of the Earth, it is basically very small, right? But it's not going to be 0, right? You are still in the orbit of the Earth. So you are still feeling the gravitational acceleration of the Earth. Okay? Okay, so let's move on. Yes.
So I thought we were still explaining why we have 0G.
Go ahead.
Well, since we have horizontal velocity, will we not have an angular acceleration outward the effects of gravity, you return back to Earth.
There has to be some sort of horizontal velocity.
Yeah, that's that's a good way of looking at it as well. Okay. So let's actually, for the next part, let's watch an n-body orbit, right? We're going to start with on YouTube, right? See, we use a lot of learning methods. An n-body orbit. Let me bring this down. We're going to start with a two-body orbit, which is the topic of this chapter. Then we're going to move on to 3 and 4 and more. Doesn't have to be a circular orbit. This is something we will talk about later. But this is one of the types of the orbit, right? It's a conic. The orbit is supposed to be a conic section. So circular orbit is also a conic section. Can also be a conic section. Then elliptical orbit, which is the most general type of orbit you are going to see. The eccentricity vector is something that you are going to see either in this lecture or the next one, which is a very important part of your orbital determination, if you will.
So the
eccentricity.
Eccentricity. Is that what's keeping it not in the same?
No, not necessarily, but we'll talk about it. Let's actually, this is going at a very slow pace. Okay, let's actually do that's the center of mass at rest. So we are not assuming that one of the masses is not moving. We are assuming the center of mass is the thing that is not moving. This is how you will see the orbit. Equal masses, though. Something that we are going to see is a hyperbolic encounter. That's what they call here, which is not necessarily an orbit. It just gets close and moves away. Three-body problem. See? A very simple type of orbit. Very simple. So hopefully, if you have enough time, we'll get to analyze this type of orbits as well. And you're going to have a lot of fun analyzing this. So let's actually move to an n-body orbit. I guess we can't really figure out anything from this picture here. Okay. Let's go back to the lecture. Before moving on, or in the process of moving on, we have to introduce a new parameter that is introduced in your book. It's the potential energy of the gravitational force, or potential of the gravitational force. Let's call it F. We define this as V equals to Gm1 M2 divided by R. And if you have this potential, you can find your F by taking the gradient of this V. Taking the gradient of this V. Okay, it's just a definition of a potential of the energy. And let's actually rewrite these equations of motions, R1 and R2, that we have on the other side of the board. Just simplify them. And I'm going to ask you to tell me how we got to this form of the equation. Okay. So R1 double dot is equals to G M2 divided R vector R divided by R to the third. How did we get from this to that equation? And this is M1, M2. It's just a mathematical manipulation. These two cancel out. UR, we replace it with vector R divided by R, the magnitude of the vector. Just so we're going to get R divided by R cubed and M2. We do the same thing for the other thing, and that's it. Okay, let's see where we are. What time is it? This equation is a nonlinear second order differential equation. We can actually, instead of using the position vectors, we can actually use a distance vector, distance between the two bodies. Find that acceleration. R double dot is going to be equal to mu divided by R3. Mu here is called the gravitational parameter. Mu. Gravitational parameter. And since we are dealing with R here, the format of this small r here, the distance vector, the format of the equation is going to be different. And we can define mu as G M1 plus M2. Gravitational parameter. So final equation of motion in a two-body problem, which is a nonlinear second order differential equation, is equals to this. R double dot equals to mu divided by R cubed multiplied by an R. And a reminder from chapter 1, from chapter 1, we can have the R double dot from the equation we had as the following equation, where R double dot will be equal to R relative double dot plus the rest of fun equation, omega dot multiplied by cross R and omega cross R minus plus 2 omega R dot relative. Okay, equation of motion, we have everything here. Let's see why. We can actually write this equation of motion, these equations, as they relate to the center of mass. Okay, so two bodies, their center of mass. This is going to be R vector, This part of it can be R1. This part of it can be R2. The whole thing can be R. We can actually write the equations of motion for this as well, in which R is equals to R1 is equals to the subtraction from R minus R2. Or no, the weighted average. So R1 is equals to negative M2 divided by M R2. We have this relationship, and we can write the equations of motion for these two. I'm sorry, I'm just running out of breath for whatever reason. Mu double prime divided by R2 squared R2, and mu double prime here, mu prime here is equals to your M1, that's the weighted average of M's, multiplied by mu. Okay, so we have the equation of motion as the distance between the two, the acceleration that changes of that distance with respect to time. We can write the equation of motion as the distance between one of them and the center of mass. We can do this for the other one as well. If we do it for the other one, that is R1. I'm sorry. R2 double dot is going to give you the same equation, negative. This time is going to be mu double prime divided by R. This is for R1. All of this for R1. R2 squared, R2 cubed for the R2, where mu double prime this time is going to be M2 divided by M1 plus M2 cubed mu. Okay, the general equations of motion. We have everything we need here to find the orbit equations. Okay. Well, how can we find the orbit equation, the final orbit equation? We actually have to start from the angular momentum. How did we define angular momentum in the previous lecture and in your dynamics? Can you, I didn't hear you. Can you speak up? MVR, that's going to be your linear momentum, right? And V is.
You just take an interval if you want to go from 1 point to
Okay. I'm not sure if I understand what you're saying, but the angular momentum was h, right? It was your r, your radius, cross product of your linear momentum, right? So it is going to be r. Is that what you were saying? Okay. R cross product of mr dot, right? Angular momentum, r, your arm, multiplied by a cross product of the linear momentum, right? And here is assumed to be constant. So r cross r dot is something we are going to end up with. Okay. Then we can move m to the other side, and can say h divided by m is equals to a small h, which is called angular momentum per unit mass. Angular momentum per unit mass. Okay. And this is equals to r cross r dot. So let's see what happens if we take the derivative of this h with respect to time. dh dt, or to find the h dot. we have to take the ddt of r cross r dot. What is this equal to? This is equals to ddt of r cross r dot, which is r dot cross r dot, right? ddt of r is r dot, right? And then plus r cross r double dot. Does this make sense? That's a derivative of a multiplication between the two variables. This is what you're going to get. What is this cross product? What is the solution to this cross product? 0, right? Any vector cross product by itself is going to be 0 because the angle between the two vectors or a vector by itself is 0. What can we say about this part? What is the equation we have for r double dot? Just a regular r double dot. It was mu. It was on this side of the board. I wiped it, but it should those equations should give you the idea as well. It was mu divided by r cubed multiplied by the vector r, right? In which mu and r cubed are just the magnitudes, so we can move them just like values, just numbers. They are not vectors, so you can move them out of this cross, right? And find this cross product as r cross r, right? So based on this analysis, what would be the result of this cross multiplication, this cross product? R cross r double dot. 0 again. What does this tell us? That your angular momentum does not change with respect to time. And we didn't make any assumptions here, right? We just use the most general form of the equation, and okay, which tells you that angular momentum is conserved. dH/dt is 0. Conservation of angular momentum. Okay. What can we conclude from this? The angular momentum is conserved. Angular momentum does not change with time. And that's the vector angular momentum, right? That's something to keep in mind. So let's say we have this body M1 and this body M2 orbiting around it. We define angular momentum as r cross product of m r dot, right? R is in this direction. That's the vector r. And vector r dot in this direction, right? It is not necessarily tangent, but station. What is the direction of, let me actually change this direction a little bit. Not a top view. Let's make it a semi three-dimensional thing, right? So this will be your r double dot. What would be the direction of h? That's the cross product of r cross m r double dot, r dot, right? Perpendicular to this plane, right? So unit vector h is going to be this, right? Unit vector h is your vector h divided by the magnitude of that vector, right? So we say the angular momentum is conserved. What does it mean for this unit vector? The direction of its magnitude is not going to change. It's always 1. What does it mean for the direction of this unit vector? That doesn't change as well, right? The vector, the conservation of angular momentum tells us the vector angular momentum doesn't change, not just the magnitude of it. So this unit vector doesn't change, which tells you that the two bodies that are orbiting around this orbit, two-body orbit, lies in a single plane. Okay. So you can always identify a plane, just a plane that your body is orbiting around your, like Earth, whatever, the center of attraction. We call this the center of attraction, the main body. So what does this mean for velocity, for r dot? This essentially means that your r dot is always has two components, the perpendicular or normal component and the tangential component. Okay, let's actually, your book calls this V normal. I'm going to follow the same. V normal and VR. So velocity in the radial direction, velocity in the normal direction, right? Wherever that is. Okay. Is there any questions? So conservation of angular momentum is very important to us because it tells us that the orbit, two-body orbit, lies in a single plane, and one of the conclusions of it is that your velocity is going to be only having two components, right? Radial and the normal component. Is there any questions from this? We will talk about embodied problems, but let's talk about them later, right? Because there are a lot of other complexities. But the conclusion of conservation of angular momentum in a two-body problem orbit is going to mean this, that it lies in a single plane. Okay? So we can also show that the area, let's say this is your M1, M2, and it has moved a bit. And this area is called the swept area that is swept by the movement of this M1 around M2. We can show that dA, if that area is A, dt is equals to h divided by 2. Okay? The idea is h is conserved with time. Okay? So what can we conclude from this equation? And I didn't go over the proof of whatever of this equation, but this is the equation we can get from the angular momentum equations, right? So since the angular momentum is conserved, what can we conclude about dA dt equals to this? So dA dt, this essentially means that dA dt is going to be constant, right? So an equal area will be swept in the equal time. That's the idea, right? dA dt is constant. So if you go from this to this at time t1, and you get area A1, then you are going back and you sweep this area A2 at time t2. If A1 is equals to if A2 is equals to A1, T1 is also equals to T2. That's the idea. Yes.
So using this, we can prove that speeds vary at apogee and perigee to keep this condition true. Right?
I didn't hear you.
So using this condition where the change in area is the same all throughout the orbit, we can prove that the speeds at apogee and perigee vary to keep.
We will get there. Okay. We will talk about all of those things. Okay. So you already know orbital mechanics then.
I did this too. Just simple.
Just simple. That's all right. Okay. We will talk about it. We'll actually, that's the discussion we're going to have in this. But what is this? What do we call this law essentially? Equal area is swept in equal time. Which Kepler? We have many Kepler laws, right? That's the main thing. This is the second Kepler's law. Okay. And dA dt is called the area velocity. So your area velocity is going to be constant. Okay. I wanted to discuss a lot more things, but I don't think we have enough time. Let's actually let's see where we can get in 5 minutes. If you use the conservation of angular momentum and all of the other long form equations we have had, not all of them, some of them, you can get to this format of the equation that tells us that R dot cross H is minus mu, that's your gravitational parameter, R divided by the magnitude of R is equals to a vector C, or a constant vector. This vector C is called the Laplace's or Laplace constant vector. Laplace vector is called Laplace vector. But it's a constant value. The vector does not change. It's also a constant value. And this analysis and the conservation of angular momentum is eventually going to lead us to the main orbital equation for the two-body problem. Let's actually, I guess let's stop here. Yeah, let's just stop here as long as you understand this part, this equation, conservation of, and also the conservation of angular momentum and the swept area, which you already know about. We will continue the discussion on the next lecture, which is going to be the Tuesday. No. Laplace transform, no. Whenever you hear Laplace, you start shivering, huh? No. That's actually, it is going to become much simpler for the most part of the class. And then it is going to become much more complex if you have enough time. So, but I would love to cover all of the book if you had enough time. But I don't think we're going to have enough time. So let's wait here. We are going to find the main orbit equations, and we will talk about the different parameters in the main orbit equation in the next class. We will talk about different types of orbit, the circular orbit, the elliptical orbit, parabolic and hyperbolic orbits. Or the movement, parabolic and hyperbolic trajectories, if you will. Because parabolic and hyperbolic are not going to be orbits anymore. It's just going to get close and move away. And that's how we actually analyze the real satellite movement outside of the Earth, right? Yeah, I guess. So that's it. That's it for today's class. I'm going to see you next week. Hopefully, with the graded homework, exams, all of the things that needs to be graded by then. So you have an idea. Do you know what is the date for the last day to drop a course and not get a WF? I think it's definitely after Tuesday, so I'm going to post all of the grades in case someone wanted to do. I don't see how anyone would want to drop this course, because I mean, there may be some people who may get an F. I don't know. I usually have an F in one F in all of my courses, but it's usually the mechanical engineering student. We don't have any mechanical engineering student. Yeah, no, I'm sorry to say this, but that's true. Except for the lab